want to introduce to you the concept of the Beer-Lambert, or Beer's law for short. As I keep saying, if you are in on a scientific discovery, it's probably better not to be the second person because their name often gets left behind. Anyway, Beer's law, as we call it, is a very simple concept that when you have solutions, that the amount of light absorbed by the solution, the amount of light absorbed, which we're going to call capital A, is directly proportional to its concentration, and the concentration we call C when listed in units of molar. And these other two factors here, A and B, A is what's called the molar absorptivity. It depends on both the wavelength and on the particular chemical species. And this is something that comes from the absorbance plots that we saw way back in the color and light unit, where if we have a plot like so, where we have the absorbance A as a function of wavelength lambda, and the wavelength generally goes from about 400 nanometers, so it's going to be in nanometers, up to about 700 nanometers. If we have a particular solution that, say, has this absorption spectrum, this is a typical absorption spectrum that you might see, that you would want to measure the absorbance. You'd want to use an absorbance down in this region. So between 400 and 700, that's going to be at about 550 nanometers. And so you can see why it's going to be important for you to indicate what the wavelength is. So you always want to indicate the wavelength when you're making the plots that I'm going to tell you about. And B then is going to be the path length of the light going through the sample, and that's pretty standard as a unit of 1 centimeter, because if you remember the cuvettes that we had, those cuvettes are 1 centimeter thick. So in practical terms, and the way we're going to make use of it, we're not really going to care about A and B per se. Like I said, B is always 1 centimeter, and A depends only on the wavelength. And I'll tell you about what the wavelength is for the lab that we're going to be doing when we talk about the lab itself. The practical use of this is that we can make what we call a calibration curve. Now, the curve is really a straight line. For some reason, scientists call all plots curves. From a group of standard solutions of known concentrations, and then based on those standard curves of known concentrations, we can rearrange this equation, A equals M times C, where M is the slope of the best fit line, and that equals the A times the B above. Nothing to do with the B that we call the y-intercept. And we're going to basically ignore the y-intercept. In your lab, it should be very close to 0. And it just comes about because sometimes the data aren't exactly as precise as you want them to be. So here's what a data plot would look like. So some equation, and for some substance, we shine incident light onto a sample, and then some lesser amount of light comes through. In terms of scientific terms, we call this I0 for the amount of light that gets through, and the I0 is the amount of light that's on it that gets transmitted, and that gets shown on the sample. And then I is the amount that's transmitted. And there's a relationship between the I and the I0 and the absorbance. We're not going to worry about that. If you really want to know about it, you can ask me, and I'll be happy to explain it. But essentially, we're going to be looking for what is the concentration of an unknown solution. So you're going to be plotting up the data from our lab on a data plot. You're going to be using Google Sheets to do so, and you'll have a template to help you get the data right. And you're going to be plotting absorbance, which is unitless. So thank goodness there's no units on absorbance. And on the x-axis is going to be the concentration and molarity. And then the idea is once you've established and drawn the line and gotten the slope and gotten the equation for the line will be something that comes right out of the Google sheet. Then you can rearrange that equation, and if you have a solution that you know the absorbance of that solution, if it's the same chemical, obviously, then you can calculate the C using A divided by M, the slope of the line. You get the concentration of the unknown. Or you can just use a straight plot where you measure the absorbance of the solution and just come straight over to the line, and wherever that line is, come straight down, and then you would find what the concentration is based on that absorbance. We are going to be using, I believe we're going to be using the slope. I don't know, I don't remember. You may have to use the sketch it out as well, but I don't think so. So we'll be using the slope to get the absorbance of a reference of just some random absorbance solution that I gave you. And for the aspirin, we're going to be doing the same thing, except I've given you what I know to be the slope of a line for the salicylic acid and iron complex. And so you're just going to use that slope of that line, to find out what the concentration of your salicylic acid was in your solution, and then using straight concentration to moles to grams, you're going to figure out how many grams of the salicylic acid you had and what your percent mass of the salicylic acid was in your aspirin. If you have any questions, let me know. Otherwise, this is Beer's Law, and I hope you enjoy the lab.